Good evening and welcome to another webinar by Technion Australia, today in partnership with Swinburne University. Our mission is to give you, our valued supporters, the opportunity to tap into the world of our scientists, researchers, and alumni who for over 100 years continue to shape the world we live in by developing cutting-edge research, applications, and innovation. My name is Ori Danieli. I'm the CEO of Technion Australia, the representative arm of the Technion, Israel's Institute of Technology. With many of Israel's greatest inventions and discoveries credited to the Technion, it is often regarded as the backbone of Israel's claim to fame as the startup nation. In Australia specifically, we're part of a global network with a mission to support the university's scientists by encouraging philanthropic support and promoting research collaboration with Australia. I want to acknowledge our event partners today, the Embassy of Israel in Canberra, which continue to support our initiatives. We greatly value it and appreciate it. We're also fortunate today to partner with Swinburne University of Technology out of Melbourne, who very similarly to the Technion share a vision of bettering the lives not only for the local community, but making an impact on a global scale, an impact on humanity. We're fortunate today to host 4 incredible speakers who are global experts in the area of space. And I'm sure you're in for a treat. So we have today Professor Alan Duffy, who is the director of the Space Technology and Industry Institute at Swinburne University. He is here with his colleague, Professor Virginia Kilbourne, who is the chief scientist at Swinburne University. We've got Professor Ehud Bahar, who is the Dean of the Department of Physics at the Technion, and he is also the former Dean of the Asher Space Research Institute at the Technion, Israel Institute of Technology, and David Steinman, who's a Managing Director of Industrial Sciences Group and lives and breathes science space research. The way today is going to work, each of our speakers will introduce themselves and their key areas of expertise for a few minutes. That will be followed by an interview plus Q&A by my friend and colleague, David Zerman. As with all our webinars, you are encouraged to ask questions, so please click on the Q&A section and our speakers will do their best to answer. So with no further delay, it is my great pleasure to introduce to you your first speaker today, Professor Alan Duffy. Alan, the floor is yours. I hope you all enjoy it. Thank you.
Thank you so much, and thank you all for the opportunity to share with you some of the activities at Swinburne and related glimpse into what Australia is doing in space. Before I begin, I'd like to acknowledge, as we are proud to do at Swinburne, the traditional owners of the land which our Hawthorne campus and the Space Institute is based, the Wurundjeri people of the Kulin Nation, and I'd like to pay my respects to their elders past, present, and emerging, and extend those respects to all Aboriginal and Torres Strait Islander peoples. The Space Technology and Industry Institute at Swinburne really does cover the gamut of activities from the upstream. And by the way, this is a little overview because I think we'll be using a lot of these terms throughout tonight. The upstream, that is the building for space, the exciting bits of rocketry, satellites, even the launch capabilities, to the kinds of activities you might do in space, and then going to downstream, which is really the utilization of space for experimentation, as we'll hear later, but also for the information from space in the helping end users, the farmers with their fields, for example, or marine science monitoring and the like. At Swinburne, just to very quickly run through a couple of great partnerships. We are very fortunate to work with Amiro, developing surface coatings for improving the durability of materials under extreme environments, such as rockets. This is a wonderful long-standing partnership. We also have a very exciting collaboration underway with Titomic, which is a manufacturing company here in Victoria, where their patented Titomic kinetic fusion, this is a cold spray technology, is going to be used to try to create some multifunctional structures with multi-materials. So this is trying to be both lightweight, but also strong and perhaps self-healing, or have electrical conductivity built into the matrix itself. There are many opportunities to explore with this kind of technology in this partnership. Now, all of this makes for more capable rockets in Australia is has a very exciting new endeavor with Gilmour Space, which is developing a small sat launch capability up in Queensland. We then have the companies that are building and launching these satellites perhaps into the future from Australian soil with Gilmour, the likes of Fleet Space and Myriota. And really they are connecting up devices around our very large yet sparsely populated nation, allowing remote asset management, monitoring, the ability to know what level of water is in tanks across a distributed farm. When some of these farms can be the size of small European nations, this is a non-trivial task. So we use satellites to relay that information. Now, of course, you can also take from space imagery, and this is perhaps more traditional use of space, or at least well known. Here in Victoria, my colleague Peter Moore at La Trobe University was a partner with the DLR in developing the Earth Sensing Imaging Spectrometer DESIS, which sits on board the International Space Station. Wonderful camera, really the Rolls-Royce of hyperspectral cameras, some 235 channels in a range between 400 to 1,000 nanometers. I always like to give a plug though for astronomers that we got there first. So universities in Australia, through our strategic partnership with the European Southern Observatory, can access this beautiful telescope, and in particular the Muse spectrograph. And in that spectrograph, we have access to 30 times higher spectral resolution than even what the DESIS can manage. Just to say, when we in Earth observation get to that level of technology and fidelity of the data sets, the astronomers have been playing with that for decades, so we should be able to collaborate and learn from one another. And then very quickly, the opportunities that such images present. Oh, sorry, and I should have mentioned, of course, electro-optic systems and the Space Environment Research Center, CERT, the ability to monitor space. So Australia has a vast area of the Southern Hemisphere that we are near uniquely capable of monitoring, and we have to play that leadership role to support the global efforts to monitor space junk. And EOS is doing a wonderful job in that with this particular image of using lasers to improve the imagery and reconstruction of those orbiting debris. Finally, as I mentioned, you can take the images, but then you can further enhance them. Techniques including super resolution AI. Just a little shout out for Jack White, wonderful paper, he's just submitted it, demonstrating in collaboration with Planet Labs, the ability to enhance and sharpen imagery and really the trade space. What can you allow the software to enhance for lower levels of hardware? And a really nice paper that demonstrates that optics dominates everything, but you can get away with slightly cheaper chipsets, perhaps. And finally, with the data, you can take the imagery from space in optical and infrared. You can combine that with synthetic aperture radar, a technique called data fusion. My colleague Kai Xing here at Swinburne is leading. And really in a recent collaboration using some of the Microsoft software, in particular land cover, really able to do a superb job in vegetation mapping and recovery. So ability again to use space to allow us to monitor our vast continent. All of this is made possible by the powerful AusStar supercomputer. And I really do want to give a shout out to the people that make these kinds of insights possible. Those who run these kind of compute facilities. Online is of course important, and cloud compute, but it also helps if you have your own supercomputer, as we are very fortunate to do here at Swinburne. And at that point, I will throw to my colleague, Virginia Kilbourne.
Thanks very much, Ellen. Let me just share my screen. Thanks to Ellen, I think you've got a really fantastic introduction to the space industry, not only with the projects that are being worked on at Swinburne, but some of the really vast companies and projects that are being worked on across Australia. And Australia has this fantastic focus on the space industry, which has been enabled by the creation of our space agency, obviously, a few years ago. And the space agency has some really big aims. They would like to create an additional 20,000 jobs in the next, say, 7 or 8 years. It was 10 years originally. And also triple the size of the industry. So what we've done at Swinburne is thought about how can we look at this from an educational model? Who is going to be in those 20,000 jobs that aren't in them today? We realise that graduates are partly going to be the answer to this, but not the full answer. So what we've been doing with a team at Swinburne, including Kim Ellis, who is our astronaut candidate at Swinburne, and Dr. Rebecca Allen, is designed a new space education model for multidisciplinary education. So I'm going to talk about that a little bit now. So space technology is a really vast field, and you've already heard that it can cover things as diverse as manufacturing to IT to even marketing and business skills. And so what we've done at Swinburne is created a suite of subjects, which we're calling a co-major, which any of our students in undergraduate can take alongside their normal degree. So we have physics students who come in and they'll be doing their normal Bachelor of Science and majoring in physics, but also majoring in space technology. So they'll learn how to apply their physics skills to space technology, and half of their course is working with industry. So they're working with industry to build up the industry in Australia. But physics is the obvious example. Where else could you work in the space industry? How about health? Health is a hugely important area for space. So we have, just recently, we have astronauts who are not astronauts going into space. So we're just thinking of the CEOs of very large companies. They haven't trained for many, many years and had all the health checks that you would normally have as an astronaut. And as we're moving into the next phase of Moon to Mars missions and going back to space travel a little bit more, and also having space tourism, we need to understand the effects of space on human health. How about business skills? And if you have a look at any of the startup companies, you'll see probably in equal numbers the number of people they're trying to hire in engineering as in business. It is a really big and important job to be able to fund the space activities and fund them in a way that is going to address the problems very quickly. So sometimes we need quick funding. We need to have lots of funding. It's expensive to go to space. So you really do need those business and marketing analysts. So we have a course where we have students from right across the university coming together and working together on projects in the space industry. And I'm very happy to say that our second course is running this semester, and we have actually seen that. We've actually got students from arts and games development, as well as engineering, robotics, IT and physics. So the other area that we might be able to help in trying to get those people into jobs in Australia, I guess, and building that space industry is through upskill of the current workforce. So we've got a fantastic range of people with lots of different skills in Australia. So lots of engineers, lots of researchers, and many who would like to work in the space industry. And so the second part of our training is around offering bespoke courses for the current workers to switch into the space industry. And what we'll see, I think, in the future in this space industry is people coming in and out of the space industry as it's required. So you may not work in the space industry for the whole of your life. You may work on a different project, say in data analytics, and then be pulled into a space project for the duration of that project. It might be 5, might be 10 years, and then you might go and work for health. You can imagine all of these very diverse careers, but how are workers going to make those changes? And so it's really important that the universities are there to help upskill our workers so that they have that diverse opportunity to create new skills and get into new industries. But the third area of education, of course, is for the younger people. So our school students, whether it's primary or secondary school, and even early childhood education, space is such an inspirational area, and it can help us attract young people into a career in STEM and ultimately in the space industry. And at Swinburne, we've been working with a local high school, Haileybury College, who has been working with us to design, build and send experiments to the International Space Station. To date, we have sent 3 experiments to the space station. And the exciting thing about this project is that it's a collaboration with the high school students, and you can see a couple of the students here in these images. The high school students are the ones who decide what the experiment is going to be. And at Swinburne, we then say, okay, you would like to do an experiment in this particular area. We have the experts, we'll help you build it. We'll 3D print the parts that you need, and we'll help you launch, but it's up to you to do all of the documentation, work on the NASA requirements, and make sure that that experiment can go into space. So I can tell you about a couple of the experiments that we've already sent and the wide variety of student ideas. So in our first year, we had a team who was incredibly ambitious and wanted to test magnetorheological or MR fluids in space using an electromagnet. This was a huge engineering challenge for us, not only because it was our first year sending experiments to the space station, but because we have very strict power and magnetic field guidelines that we have to adhere to, of course, when you're sending something onto the space station. However, the students did a fantastic job, and we actually had a working prototype by the time we left Earth. But we did learn something in the launch, which is make sure that your moving parts don't stick when they're under high Gs. And so unfortunately, we had a little moving part that was meant to move once you got into microgravity, and it got jammed on launch. So everything else worked perfectly, but unfortunately that was jammed. But we learned a lot from that experiment. And look at the team there, those absolutely fantastic students who built this experiment from scratch. So the second year we thought we'll do something a little bit easier. We won't have a moving part. We've got, how about tooth decay? And that's a huge issue, of course. So we already know from previous experiments in space that bacteria grows very, very well in space. It actually really likes space. And so we wanted to see, how does bacteria grow on a tooth, and do you see accelerated tooth decay in space? So this experiment worked very, very well, and it got the whole school engaged. So Haileybury is a prep to year 12 college. So that's having about 5-year-olds to 18-year-olds. And what the students, the high school students, said was, they put a challenge to the primary school students and asked them to send in their teeth as they were losing their baby teeth. And so we ended up with a big bag of teeth, but beautifully, one person lost 2 teeth. And so at the same time, and so we could have a control on Earth and a control in space. Now, to make sure everybody stayed excited, we didn't tell the students which tooth we sent to space. We said it could have been yours that went to space. And so that really excited the whole school about this project. The really interesting thing about this experiment was that we put 1 bacterium strain into our experiment, and then when we analysed it, when it got back to Earth, we had 7 bacterium strains in the sample. We think this is due to cross-contamination rather than some sort of space bacteria infiltrating our experiment. However, you never know. No, I think it really was actually something that we did on Earth. But once again, we learned that we didn't do this experiment in a clean room, although we were all gowned up, as you can see in that experiment there, in the image. And so that we really learned that bacteria is everywhere and it can get into your experiment. So if you're doing this sort of experiment, you have to really be very careful.
You've got about a minute, Virginia.
Sorry?
About a minute to go.
Yep, no worries. Our third experiment is we sent some chia seeds, and we tried to grow chia seeds on the International Space Station. And this all worked very perfectly, except the experiment next door to ours ran hot at about 50 degrees. And so unfortunately, our chia seeds didn't like the heat, so they didn't grow. So maybe I can just finish with, this. We've found out that these projects provide work experience, project management, and leadership skills for the students. And we're expanding this to be a nationwide project next year, thanks to the SmartSat CRC initiative. So if you're in school, or if you have children in school or know of high school kids, watch this space, because you might be able to send an experiment to space as well. Thank you.
Thanks very much, Virginia. As we said before, Virginia is the first chief scientist at any university, and congratulations on your recent appointment and all the very best. Our next speaker is Ehud Bahar, who is Dean of the Department of Physics at Technion and was previously Dean of the Asher Space Research Institute at the Technion. Ehud, over to you.
Can you see my screen, or is it? Yeah, we're good. So hi, everybody, and thank you for joining us today. For the precious few of you who don't know the Technion, I just want to say a few words. Technion is the Israeli Institute of Technology. It's actually the first university in Israel, and still the leading technological and science university. We like to brag that we have more Nobel Prizes than any other university in Israel, but these are all small numbers. So stay tuned. Another thing that most people don't appreciate about the Technion is that all our graduate programs are in English, and we welcome applications from all over the world. In normal times, I would invite you to come visit. I know today is harder than it used to be, but we like visitors a lot. And if anyone in the audience is interested, please don't hesitate to ask us. Yeah, our students don't only study, but they also party, as you can see. But let's talk about space. The Technion was one of the first universities to build its own satellites back in the 1990s. The TechSat was launched, and I think to this day holds the record for the longest living operating student-built satellite. It worked for 12 years, and from 1998 to 2010. Very recently, just in this last March, we launched 3 satellites in a mission of swarming what are called nano satellites, about the size of a shoebox, that are supposed to fly autonomously and geolocate sources, radiation sources on the ground, for instance, for safety and rescue missions. Virginia correctly pointed out that space is very expensive. And in many cases, it's above the budgets that we usually have at the universities. We have to thank our friends overseas, starting with Australia, of course, but also in the US and in France. These missions would not have been possible without philanthropic donations of our dear friends overseas. My last slide here is going to be about private missions in space, but the Technion for many years now has been using very generous private money to actually get our students acquainted with the space technology, which is very difficult for universities. I'll take a step back and mention something about the country as a whole. Israel has been in space for over 30 years, starting in the 1980s. We like to think of ourselves as one of the 10 nations in what is called the Space Club. Israel develops, builds, and even launches its own satellites for many years now, mostly Earth observing. These are the OFEC satellites and the EROS satellites that are the commercial version, but also communication satellites, the AMOS line. And Alan mentioned SAR. Israel also built its own synthetic aperture radar observatories. I like to highlight this one Technion satellite from the 1998, much smaller than all the others, but was, I think, a stepping stone in the development of Israel's abilities in space. These are a few images that are publicly available from Israeli satellites. You can see the high imaging resolution. I don't know if you can see these players on the football field. This is the Holy City in Jerusalem. And the joke here is that our telescopes are so good that we can tell the difference between men and women. We can tell gender from up in space. And of course, that's only because they're separated next to the Wailing Wall. You might see these kinds of images in the news, not as high resolution, by ImageSat International, which is an Israeli company that commercializes the technologies that are primarily funded for security and for defense purposes. This is a totally private company, and we get these images on the news regularly. Again, I've seen them on CNN. I've seen them on newspapers all over the world. For us, it's mostly a demonstration of our technological capabilities. Recently, and I think that's the case in Israel and many other countries, we're trying to take the huge government investment in defense and try to do more interesting things with it. Israel, together with France in this case, built a satellite that's called Venus. It's a misnomer. It's a very bad name. V stands for vegetation. Has nothing to do with the planet. It's an Earth observing telescope, and it studies vegetations primarily in the Mediterranean, but all over the world, of course, because the satellites orbit Earth. There's a Technion contribution there. This is the first time on an Israeli satellite that the satellite is using what we call electrical thrusters. Those are plasma thrusters using basically solar energy to maneuver the satellite. Clean energy, very efficient. This thruster was developed at the Technion and later built for this mission by the Israeli industries. There's a follow-up mission called Ciel for cloud research. The idea is to build 3 satellites and to image clouds from above. I'm not an environmental scientist, but I'm being told that the evolution of the top layers of clouds has a lot to do with the way they end up producing rain or not, and hopefully with sophisticated imaging from 3 different satellites, again, in collaboration with CNES, with the French Space Agency, the Technion will be able to build this mission that right now is only on the drawing board. I want to give a few examples of technologies that are being developed at the Technion. I have to make this distinction between what the industries do, they know how to do, and what the university does, which is looking maybe 10 or 20 years into the future, and maybe some of the technologies we're experimenting with will end up in the industry, maybe not. One example are these folding telescopes. We have a laboratory that's been experimenting with distributed mirrors to create a better image than is possible with smaller telescopes. For astronomers, that's obvious. Size matters, and you want to launch as large a telescope as you can. When you go to space, you're always limited by the launcher. So you see this movie running, the video running shows you how you can fold the telescope and then unfold it up in space, get a larger telescope than you are able to launch today. These movies show how autonomously the mirrors kind of autofocus and give you the sharpest image, despite the fact that they're built from several segments. Another nice experiment we did is to track geostationary satellites. The communication satellites are these satellites that pretty much stick at the same point above Earth. And with an amateur telescope that you see down here, we were able to see these satellites. Basically, you see their solar panels, the sun being reflected off of their panels. Astronomers know that telescopes need to track the stars in order to observe them because the stars move in the sky. You see the stars passing by. This is a fixed telescope that can't image stars, but it can image these satellites and monitor their, they do have some trajectory. They do move around a bit. And the motivation here was to find the most efficient way to maneuver them in order to save fuel, because that basically determines the lifetime of these satellites. So Amos 2 and 3 that you see intermittently are two Israeli built communication satellites. And in the image down here on the right, you see the stars. If you close and open the shutter, the stars come up as these bars, and the two satellites are seen very clearly. They're not. So this is really a nice example of an experiment that we built with students and high school students with an amateur telescope on the roof of our institute. Going further into outreach, in 2016, we hosted something that's called the International Space University. It is a traveling university that goes to different venues every summer. In 2016, we were fortunate to host it here. It's like the Olympics. You apply and you compete to host the event. And then you need to spend a lot of money, of course, to make it happen. It's basically the summer program is more than 100 students, and I call them students, but they're basically professionals in the space business. Some of them are real students, some of them are government officials who come to the university for 2 months. We hosted them for 2 months in Haifa, and get dozens of lectures and projects, and write white papers at the end about a whole slew of space topics, not only space research or space technology, but space law, international relations, and so on and so forth. What you see on the left-hand side are the students of the ISU spelling out ISU on our lawn. This is the Technion lawn, and this is the image from space of these students on the lawn. That is black and white. That's the limitation of the satellite that we were able to harness for this image. My last two slides are about private initiatives in space. You may have heard about Space IL, and I know that David will talk more about that later. Space IL, but I'd like to tell the story. Space IL started with these 3 kids that you see here. They were much younger than they are in this picture because it took several years to build the satellite. Basically, none of them had any experience in building satellites, but they heard about the Google Lunar X Prize that offered $10 million for a private venture that will build a satellite that will launch on the moon, launch to the moon, land on the moon, and even hop and send back an image. They initially thought that $10 million is a lot of money. For me, it was obvious that these people at Google have no idea about space business, because it costs maybe 10 times that much if you can do it efficiently to get something on the moon. But anyway, they had this dream, and they came up to me back then, I think this was 2012, and said, look, we don't even have $50,000 to sign up for the Google competition. We gave them some money just so they could sign up, and they started thinking about how do you get the moon, how do you build something that will actually land on the moon. Turned out to be more than $100 million of a mission, almost completely funded from private philanthropists. This is our visit to the integration room at the IAI. I should have said the main Israeli industry building satellites is the Israeli aerospace industries. This is their clean room, and the satellite or space craft, I should say, going to the moon is right behind us. And I don't know if you can read this, but this is a real image from the lander as it was approaching the moon, saying small country, big dreams. Unfortunately, they didn't land safely. They crashed on the surface of the moon, which you can see here on the left-hand side. But as Virginia told you in space, you learn from your mistakes, and you learn from how things don't work properly, and hopefully you come back next time and you do a better job. So the next mission, which we call Bereshit 2, yeah, I forgot to say, Bereshit is Genesis in Hebrew. Bereshit 2 is already raising funds. They've raised, I think, more than $70 million, and they have a plan now to have both an orbiter around the moon and this very ambitious 2 landers. And hopefully, they're talking about launching in 2024. That's very optimistic, but hopefully we'll see Bereshit 2 being developed, designed, and built in the next few years in Israel. Another thing that you've been hearing quite a bit about in the news recently are private astronauts, people paying a lot of money to go to space. We're fortunate to have an Israeli who has enough money to buy a ticket.
Just a minute to go, Ehud.
What's that?
A minute to go.
A minute. That's fine. I'll use less. Eytan Stibbe, what you see here in the red shirt, is going to go up to the space station and offer to take Israeli developed experiments to the space station, both for research at the universities, but also for education. A lot of high schools are taking part in this mission. And 3 examples from the Technion are a gamma ray burst instrument. Gamma ray bursts are these explosions in the sky that astrophysicists like myself care about. There's an experiment to test what we call a nano thruster, a tiny thruster that will propel these nano satellites. Nano satellites basically don't have good viable thrusters that allow them to maneuver. And there's a Technion professor who developed these, and hopefully he will be able to test his thruster in this mission. And another exciting experiment is an experiment to fabricate optical lenses in space to use fluids. The idea is that to build a large telescope on the ground is both expensive, then hard to launch. It's very heavy. If you could fabricate your telescope in space, you can build basically any size of lens that you want. And there's a Technion professor who developed this technology, and Eytan Stibbe, which you see here, the astronaut, is supposed to fabricate the first lens on the space station in space from fluid. That's it. Thank you very much.
Thanks very much, Ehud. And now it's my pleasure to introduce David Steinman, and he'll be giving us some information about things that maybe some of you had never thought of. Thanks, David.
Just all right. Just get our screen sharing. All right. Do you see the slide on the screen? Do you see it? Yep.
Yep.
So I'm going to talk about some exciting times in space. It's been a pleasure to hear from my academic colleagues, and I'm aware that I'm the last
David,
one here, so I'll try.
I'll just
David,
interrupt you.
if you
You
could
might
just
want to hit present mode.
Yes,
We're seeing your slides and notes and everything.
we're seeing the other slides.
Oh, right. Sorry. Yep. Thank you, Alan. Is that better?
Yes. No.
Go up to
All
display
right.
settings. No, wait, one more. I've done this so many times myself. If you go to display settings, the one in the middle.
Is it not displaying now? Yep.
It's displaying your presenter notes. So you just hit display setting and then swap. Yeah. There we go.
Even on the ground, we can have malfunctions. Thank you. So I'm going to be talking about exciting times in space. It's been good to hear from our academic colleagues. I'm from a company and my own business where we work in mathematics and statistics on many sectors, the biggest one being space. So we're not building rockets, but we're involved in navigation. We're involved in modeling, simulation, trajectory design, things like that. I'll talk very quickly how I got into this. We were directly involved in the Bereshit mission. I'm wearing the mission shirt. We're involved in some NASA missions and the Australian Space Agency. And I'll talk a little bit about our work in space junk, which might be of interest to everybody as well. So how I got involved was that maybe like some of the audience, I'm old enough to remember the Apollo moon landings, which are very exciting. There's Buzz Aldrin walking on the moon on the left when I was a little kid. And I was very lucky to meet him as I presented at a conference on our work in statistics in space with my partner Kelly, and you can see Buzz Aldrin on the right there, now a bit older, but still a great moment. So people ask me, what can you do with maths, particularly if there are younger people in the audience or parents with children. We work, just so that you know, in many industrial sectors using maths and statistics in the real world, in the very real world. And I'm only talking about one topic tonight, which is space and astronautics, but there's a wide range of things to do, which is shown up here on the screen. But also I and many of my colleagues in my business are engineers. So, and what is engineering compared to science? This is a very famous quote from a great Hungarian Jewish man who was an engineer and a scientist, Theodor von Karman. And he explains the difference between engineering and science up here, which may be of interest to some of you. So Ehud has already spoken a bit about the background of the Space IL Bereshit mission, so I won't repeat it, but he's right, it did take a long time. And it started from a small design and went up to its final design. All up though was still a great achievement, the first private spacecraft to ever leave Earth orbit and orbit the moon and land on the moon. There you see it now, being covered in gold foil. It's atop an Indonesian geosynchronous satellite that was being launched, what's called rideshare, where we're like hitchhiking on a bigger satellite to go into space. Interestingly, Israel and Indonesia don't have relations, but they could go up together in space. We were involved, as I said, in navigation, understanding where is the satellite exactly. In space, there's no roadmaps. There's a lot of complex mathematics, statistics, probability, simulation, and computer work around knowing where you are navigating your way into space. To do that, you have to track your object. We're involved with the ground station network, which was from all over the world, including 2 stations in Australia, with the company called SSC, which was tracking the satellite as it orbited the Earth and then went to the moon. Now, the trick is it's not easy to get to the moon, especially on a very low budget like what Bereshit was on. So you do loops around the Earth, as it's shown on this slide here, and then you have to capture the orbit of the moon exactly at the right time, exactly at the right speed and at the right angle to then enter the orbit of the moon, be captured in the moon's gravity, which is called lunar orbit insertion. If you miss it, you go past the moon, you won't get there. So for those who are a bit more technically minded, what we did was do a lot of pattern analysis, time series. We're working on things called residuals, which is the difference between where we expect the satellite to be and where the data was telling us where it was. There was a lot involved. It was rotating, antennas were not set perfectly, bore-sighted. So we had to do a lot of analysis with what's called orbit determination to help them understand what orbit we're in, which is essential in order to get to the moon. Other things here to do with pattern analysis and signal to noise ratio might be relevant to some in the audience. But basically, it was a success. We got to orbit the moon. As Ehud pointed out, there was a malfunction only in the last about 500 meters to kilometer above the moon. It was a software malfunction that basically caused a reset due to the inertial navigation unit. And then the engines turned off. They did turn on again, but unfortunately, it was too late. We're accelerating, came down, hit the moon pretty hard. But anyway, mostly a success. This now become a great inspiration to people all over the world, including NASA. So we are now working with NASA and companies who are now doing more privately funded missions around the moon or going to the moon. Astrobotic, we're working with landing on the moon. This one up here is called Rocket Lab Capstone mission, which is going to be orbiting the moon, or a CubeSat, which is a small 10 by 10 by 10 centimeter module. And it's going to be in a special orbit, which is always in called a halo orbit, facing the Earth. And it's going to be a part of the communication system that's going to lead on to what's called the Lunar Gateway, which is the next step, which is where we're going to have a station going around the moon permanently. It's going to have astronauts that can go down to the moon, and also it's going to be a stepping stone to go to Mars. So the exciting times ahead in this one, and particularly on the navigation and everything around it. We're also involved with space junk. It's something you hear a bit about. There is unfortunately some junk in low Earth orbit in space, which is bits of old satellites, bits of pieces that were thrown out there, which are just keep orbiting. And if you're orbiting around the Earth, you're going pretty fast, 28,000 kilometers an hour. Whether it's a screwdriver or a fleck of paint or an old satellite, it's going roughly at that speed. And if it hits your satellite, your Optus satellite, or your telecommunication satellite, it'll stop you watching the Olympics because it's going to smash into it and blow it up, smash it up. And then when you have more junk, you have more opportunities for more collisions. So we're involved, there's 28,000 objects being tracked above 5 to 10 centimeters, but there's millions in the very small range. We're involved with a project with the funded by the Australian Space Agency and NASA to work out, again, this uncertainty. Where exactly where's our satellite, what's called the primary, and where is the debris, the object of rubbish or space junk, so-called. And then we need to make a maneuver decision. Do we maneuver out of the way or do we not? Remember, there's no fuel stations in space, so we have to conserve the amount of fuel we have on board our satellite. So we're involved in what is the probability of collision, when should we move, when should we not? And of course, nobody wants to make a mistake on that. Finally, on the space junk issue, there are other ideas like using lasers to fire at a piece of debris and push it. The laser's got photon pressure, push it out of the way. This is a project that's it's ongoing. We're involved in the simulation to work out, can it work? And we prove that yes, it can. Basically, you can push an object into a new orbit out of the way of a satellite. So these are other options to do with the space junk thing, and there are many other ideas as well. So I think I'll leave it there, as I'm probably up for time, and there's maybe people want questions and things like that. Thank you very much for your time, everybody.
Thanks very much, David. Really appreciate it. And thanks to all of you. I'd just like to ask a question for each of the presenters. Was there anything that you heard from one of the other presenters that you might have thought, wow, I didn't realize that, or that's really, really interesting? Who'd like to go
I'm going to
first?
jump in. I'm going to jump in. So Ehud, well, everything you showed was amazing. You've now made me realize the selfie I need my institute to take is now from space. So that's extraordinary. So thank you for that challenge. I think all of the technologies you demonstrated were truly impressive. It was what I have an immediate action to follow up about the folding telescope. We have some very interesting collaboration opportunities, but it was actually with David and your space debris maneuvering insights and capabilities. I think that's extraordinary. I was not aware of that at all, to my shame, but this is what these kind of events are all about. So I'll be in touch. We're doing something that could be of interest.
That'd be my pleasure. I was fascinated by Mehud, just at Israel's long history of satellite technology going back to the 80s. It puts Australia to shame, but kol hakavod. It's very impressive.
I'll jump in and put things in perspective. Okay, we're a small country. As an astronomer, I've always envied Australia with their heritage of astrophysics and radio astronomy. And I think astronomy is even a better vehicle for education than space technology, because, you know, for kids, of course, they're fascinated by space, but technology can be hard. Whereas astronomy is much clearer to them, that you know, the potential of exploring the cosmos. And I think we have a lot to learn about how you do education to high school students at the university level. I have to tell you, in Israel, we're not doing a good enough job. The two systems are separate, and we don't have the resources to educate enough young kids who come up to us and say, hey, I want to visit, I want to see your labs, I want to, we've got to do a better job of bringing young kids to the university level so they see what research is about, they see what space technology and astronomy is about. I was genuinely impressed.
Yeah, I was really impressed that your students launched a satellite in 1998. That's incredible, and that it lasted for 12 years. I think that is just an absolutely huge achievement. I was also fascinated, at having a very big maths background myself, to see the mathematics and the company that you've been able to set up around mathematics, and the importance of mathematics in space activities cannot be overstated. So yeah, that was really fascinating. I loved the comment that you know, we learn so much from what is can be seen as a failure, but as you said, it's not the launch to the moon was not a failure. There was a malfunction in the last 500 meters. There's a whole lot of achievement before that one thing, and that was incredible, and how much that is now feeding into the next generation of missions. Very inspiring.
I mean, I'd be interested from academic colleagues. Kids ask me, how do I get into space? I say, whatever you do, you've got to do maths and physics, because that's the language of space. But maybe if there are young people on this call, we don't know, but maybe the academic colleagues could make a comment on that. I see that as the entry level, but you may have a comment.
Virginia, would you like to respond?
Well,
So I
I
think
say that I'm sorry, Virginia, go ahead. We say that all the time. I think fundamental math, physics, other sciences, chemistry, biology, are always the pillars of whatever you decide to do later. And I tell undergraduate students when they come here to our open days and want to decide what they want to do, I say science only open doors. You study physics, you can do anything. And we have a long list of professions that we know our graduates are in after they've studied physics. And I can tell you, from medical doctors to data scientists, to teachers, artists, a good science education is the basis for, first of all, a good life, but second of all, really a career path opener.
Virginia, do you want to add to that?
Only to agree furiously with what you've just said. And we did a survey of our science graduates a few years ago of 400 students, and there were 400 career outcomes. And it was as broad as you mentioned. I think science sets you up for a fantastic lifetime career. Whether or not you work in the sciences, having that background in scientific understanding and scientific process is really important. Mathematics and physics, if you can set yourself up in the fundamentals there, you're setting yourself up for a very strong future, especially in the technology and space areas.
If I can just add, presumably most of you have seen the movie Hidden Figures, which is about NASA in the 60s, I'll say. Focusing on a woman called Katherine Johnson. For those of you who haven't seen it, I strongly urge you to go and see it. It's called Hidden Figures. And it's not only about the mathematics required, but if you think about what's happening today and the fact that these women who were working in this area at NASA were called computers. So it's really exceptional. Alan, could I ask you, you want to tell us a little bit about your background, how you got into the area you're now in?
Yes, sure. So I did physics at university, PhD in astrophysics. I specialized in supercomputer-powered simulations of galaxy formation within a broader cosmology framework, and began to slowly find myself drawn ever more to hands-on experimentation, first dark matter experimentation as part of SABRE, the world's first dark matter detector in the Southern Hemisphere here in Victoria at the bottom of the Stawell Gold Mine, a project led by Elizabeth Barbario of Uni Melb, and then ever more hands-on into ultimately pieces of hardware that have flown. So but it all began with that fascination of astronomy and a strong mathematics, physics background. I was going to mention, actually, there are many other career opportunities within space. You can come in space with economics or legal backgrounds, for example. We just started a PhD in responsible AI in space, and the successful candidate for that actually has a legal background. So there are many ways to get involved in the space sector, but I think for most of us who have that fascination with the night sky, you just find yourself drawn there. You can go on a very wandering path, as I did, in terms of all the work that I've done, but sooner or later you end up in orbit.
Thanks. Virginia, I'd just like to ask you, your focus has been a lot on education, preparing and delivering courses. When you're at school or university, did you have an aha moment? Was there a teacher or lecturer who inspired you so much that you really wanted to get into this area?
Yes, there were two teachers actually who got me into physics, firstly. So my best friend's mother was my physics teacher, and she had a mantra of there are no silly questions and question everything. And with those two, that sets you up for a science career. And I've never forgotten that. And so that, I went through high school, loved physics, and went to university to study physics, and found out that astronomy is a career. I had no idea until I got to university. And so I went and talked to the head of astronomy at Melbourne Uni, where I studied. And she said, well, I've got this fantastic PhD project. So I was in first year, and she said, I've got this great, fantastic PhD project. We're building a new instrument for the Parkes telescope. In 4 years' time, it will be ready. So if you do lots of maths, lots of physics, and get high grades, I'll see you in 4 years to do that PhD. And so that's what I did. I was absolutely hooked. So, and it was because, she had time for a first year student who was just interested in space. So that stayed with me as well. So whenever someone comes to talk, I always pay attention and try and provide opportunities.
Thanks very much. Ehud, you've been in physics, but is there something in all the work that you've done in your career at the Technion, something that stands out, something that you contributed to, that you take particular joy in?
Okay, so speaking of career paths, when I came to the Technion, I was doing basically astronomy. I was using telescopes to explore different kinds of phenomena. And I went on a sabbatical to work at NASA Goddard for a couple of years. And I got excited about hardware, just like Ellen mentioned. I think most scientists are driven by curiosity, and curiosity doesn't go in straight lines. You get hung up on something and you say, wow, I can actually do that. And I had this opportunity to start building instruments. And what we've been doing in the past few years that still needs to pan out, but I'm already proud of, is we developed a new method to detect these stellar explosions and be able to identify their direction. The challenge with some of the explosions that you can detect them, but then you don't know exactly where they are on the sky. And that's something that hopefully we'll be building for space in the next couple of years. And you'll have to invite me again if you want me to tell you about the results, because we don't have any yet.
Thanks. David, quite some time ago, when I was doing postgraduate law, one of my subjects was international space law. And that was my first introduction to space junk. I've always, since then, been really fascinated by it. Is there a particular piece of space junk that you know of that you're really concerned about?
Wow, there's a lot up there. Well, no, I can't say there's a particular piece, but what is interesting from a space law point of view is who's in charge? And the answer is nobody. It is pure anarchy up there. There is no rules. There is no regulations. Countries like India and China have intentionally created junk up by destroying their own satellites intentionally as missile tests without any, it's like causing a car accident without any ramifications from the police. So I'd say there's a very interesting legal issue to come in international relations as to who's responsible for what piece of junk up there, which as a lawyer, you might be interested in. So a bit of a change to answer you.
I'd like to go now to some of the questions that have come through. Alan, I'm just throwing this to you because it was the first one that came very early. Are there any plans to return to the astronomy lectures at Swinburne?
Oh, me to return. Right. Yes. Look, I always drop in. I do love the lectures. I'm very fortunate to have engaged students every year. So no, you'll see me around, and in particular as we return to campus. Yeah, I'll be there.
Another question from, excuse me, just one moment. Another question is to do with, someone is asking about the Australian Space Agency, and they really wanted to know, unless you're in the field, you don't necessarily know about it as an organization. They're saying there doesn't seem to be a lot of publicity about it. Alan or Virginia in particular, would you like to comment upon that?
I would say that certainly they feel very strongly that as many people as possible should be aware of them. They're very active on the social media channels, seek the opportunity to give feedback in any number of the industry and public consultations that they routinely run. Just head to the Australia Space Agency website, and they have all of the information publicly available. Lots of reports have come out recently, and I can see even in the chat that some people are actually sharing some of those reports. Good on you, Stuart Finn. Virginia, do you want to say anything else about it?
There's not much to add other than, yeah, I think the strategy and policy documents on that website really tell you where the focus is for the space agency, and it is quite focused because it is a small entity and a growing entity, and so the best way to get value out of that is to focus on particular areas. So definitely check those out, and if they're in the chat already, the links, then you can just go straight there.
Oh, I will have to give a follow-up. The Space Agency funded and delivered the Australian Space Discovery Centre in Adelaide that was undertaken by Questacon, the nation's premier science technology museum or educational experience. So well done all the team of Questacon for delivering it. I got the chance to see it just before I got locked back down. It is a wonderful experience for any age. So do try to get out to Adelaide and see that when you can.
If I can just say, we've got I think the chair of Questacon with us in the audience this evening, and I'm sure that he will appreciate you drawing that to the attention of everyone who's here. A question, which is more important, outer space technologies or close space to Earth technologies?
It's like asking, who do you like more, your mother or your father? That's
Yeah, that's right.
That's a hard question. The nice thing about research and development is that sometimes you don't know where the breakthroughs are going to come from, and you don't want to have all your eggs in one basket. So I would clearly say both are very important.
Right.
Different.
Anyone else want to comment upon that, or?
Well, I just confirm with Edward, they're both different and doing different things. Although there's exploration, there's space communication, so they're all in different rooms. So they're not. Yes, you can't say one's more important than the other.
Karen Medalia, I think you've got your hand up to ask a question. Would you like to ask that question? You're on mute if you...
Question.
No?
My mistake, sorry about that.
That's okay. Your question. Okay. Right. I'll just go to a question from Sarah Fox, who said that it was mentioned that policy. Someone mentioned law and policy, or a couple of you have, and that's this particular Sarah's area. She wants to know what barriers have been encountered in the relationship between law and policy and the development of space.
Maybe others want to answer it, but I think there have been no barriers because there's been no policy. As I mentioned, into space debris, there is no overarching legal framework yet. That people are talking about implementing it, but so far there is none. But maybe others have an opinion.
Yeah, maybe I can
Virginia.
just add a little bit, because one of our staff at Swinburne, Kim Ellis, is a space lawyer, and she's focusing on mainly asteroid mining, actually, and that's a pretty interesting field for law. So there are some really complex legal issues, I guess, when you're looking at the individual countries' laws and how they interplay with each other, and generally through various treaties. And rather than, well, there's international laws, but these treaties are the way that they generally interplay. And so what we're finding at the moment, I think, and please correct me if I'm wrong, but it seems that the industry is moving faster than the legal system, I guess. And a really nice example of that is all of these nanosats being put into space by companies such as SpaceX. And so there is not a huge amount of regulation around what is okay to go into the night sky for humanity. And is it okay for a company to decide that all of humanity will see 10,000 satellites at any one time when you look up at the night sky, rather than looking at the beautiful sky that you might see like from behind me? And this is a really big issue for example, for astronomers, which is why I bring up that example, but there's many, many others. So in Australia, we just have some new laws and regulations around, for example, launch. And once you have those, I think putting those in place and then finding out how they work, as in when you have people that are testing those laws, so they're applying to launch and there are issues that happen and you have to go back to those laws and test them. That is a longer process than it is to develop the technology and launch it at this particular point in time. That would be my...
Thanks. Could I ask each of you, what do you think of has been happening in the last, I'll say, couple to few weeks about I'll call it space tourism, the private entrepreneurs spending a lot of money and having a good time and trying to outdo the other. Ehud, do you want to start this discussion?
Yes, sure. Well, I think the first principle is that if you make a lot of money and it's fair and square, you have the right to decide where you want to spend it. But that's not what you were asking. I understand what you're asking. I think the fact that these millionaires pay a lot of money to go into space also has an advantage for others, for us. One is the PR, right? It calls the attention of young kids, of scientists, that space is exciting. Even if these people don't do anything particularly exciting when they go up to space, the hype around it, I think, is important. The other thing is that when people go to space, there's a lot of technology involved around it. And that, for many years, I think, beyond the very basic drive that humans have to explore, has been the justification for huge amounts of money that go into sending people to space. As an astronomer, I can tell you that part of our community thinks it's a waste of money because you can build robots and telescopes and they do a better job of research than maybe a person that goes up there. But it's a basic rule of science that if you try to do something hard, good things are going to happen. And it's very hard to send people to space. So I think in that respect, I don't see a problem with people spending their own private money if that brings along excitement of youngsters and the development of technology to make that possible.
David, would you like to add some thoughts?
Yeah, I agree with Ehud, and I go further. I think it's fantastic. It's a demonstration of technology. It's an inspiration, and the prices will come down. Like these were the guys the first. Of course, they paid a lot of their own money, cost. The prices will come down. Will be more available, and it will, as Ehud said, yield great spin-offs. And yeah, people shouldn't be envious. It's something very exciting.
I want to add just a comment I forgot. There's a funny story that NASA tells. I don't know if it's true. They said if they weren't astronauts, there would be no disposable diapers. They claim that they developed the disposable diapers, and if it wasn't for NASA, we'd still be using cloth diapers. I don't know if that's true or not, but it's a nice story to see how unexpected spin-offs come off of the space research.
Well, I've just I have a 3-year-old, so that's very a story that's very close to my heart. So thank you, NASA. I wanted to continue that vein. The cheaper launch access, that increased numbers of space tourists will drive through economies of scale, through improvements of technology. That's advantageous because it means it's cheaper for scientists to get access to space and all the wonderful work that can be done up there, but also for the satellites we might launch, and in particular allowing poorer countries, not just the rich countries, to gain the access to space, the information from space. And the UN Sustainable Development Goals, all 17 of them, require access to space to deliver on. So this is a tremendous democratization of access to space paid for by private money. And that is a win-win. There's also, and then slightly idealistic, and I keep getting attacked when I put this out there, but I'm going to do it anyway, it is the overview effect. We know when we've sent up the astronauts, many of whom are military test pilots, not exactly bleeding heart liberals here, they have gone up and been changed by the fragility of the Earth as the blue marble suspended in the dark void of space. They have come back environmentally aware and charged and try to undertake efforts and actions to safeguard our planet on their return. Imagine what's going to happen if only a small number of the richest, most powerful people in history get that same effect, and they come back and use their wealth on their return to improve our planet. That is an exciting outcome. But to be honest, we don't even need that to gain the benefits from space tourism. We're getting it simply through economies of scale. And that is a wonderful law that we know will work out.
David, any thoughts on that? Want to add?
Yeah, if you all want to start a group campaign to raise money, I'm willing to be the next guy to go up.
Virginia, thank you.
Well, we have Kim, who is also a space lawyer, is training to be an astronaut on Blue Origin. So she'll do a training in September and is going to then be qualified to basically fly on these flights as a research scientist and conduct, in particular, experiments on the mesosphere. And I think there was a question about climate science in one of the chat, and this is exactly what she'll be doing. And so there's some really interesting experiments that you can do, and don't ask me to elucidate on that right now. Maybe we can have another talk by Kim at some point on those. But so, you know, it's not just the play effect, I guess, which is what we've seen with the billionaires floating around in the capsule, but the technology that is behind that, they're really developing that so that you can do really good scientific research, and that should help us back on Earth.
Thanks. Ehud, you mentioned diapers as a product coming from NASA research. I suppose my question is, leading on from that, diapers are a real problem on Earth. What about the environmental costs associated with all the space activities? Forget the diapers.
Right. I should have mentioned that NASA used to say this many years ago. I don't think they, now that we realize how bad for the environment disposable diapers are, I don't think that gives NASA any good PR anymore. I totally agree. There was a comment by Sarah Fox in the chat about do these millionaires not need to also donate or contribute to space research, to climate research? And I think absolutely. I think that could be a requirement. That's part of the way to maybe attract good people to contribute to space research, is that eventually, I mean, the example of diapers is an indirect example of how technology brings about, you know, something useful to mankind. But I think when it comes to climate, we know exactly what we need to do. And it's you know, there are big questions out there, but the practical aspects of it are very clear. And absolutely, I think people who research space, who exploit space, should also contribute and do whatever it takes to save this planet. Or we won't be able to do space research, you know, in another century or so.
I wonder if I can just take on from that, the climate cost, the potential carbon footprint, in particular of the launch that was raised by, I think, by Ori in the chat. It absolutely would. However, you can also make this, you know, a lighter footprint. So we have in electrolysis, passing electricity through water, you get hydrogen, oxygen. That is literal rocket fuel. In particular, it's rocket fuel for, say, Blue Origin, as distinct from Virgin Galactic, which is Richard Branson's launch. So in that sense, so long as the electricity that does generate, that that powers that reaction is generated through solar panels, then it has a fairly light carbon footprint. So you can make smart choices as a company to lessen one's footprint and still unleash all of the benefits from space tourism. So I think that it need not be quite so damaging as it perhaps at first glance might appear. And it's also a near infinitesimal amount of carbon footprint, even if it exploded at the most, well, unfortunate term, if it rocketed away at the greatest possible growth as a sector, it will never equate to just what we do in terms of aviation each and every day, even in this pandemic period.
That's right, and space is infinite. It goes on forever. So there's a lot of space in space, in case people were worried.
I'd like to finish up by asking each of you the same question. I'll just say it once. And you're looking forward. When you wake up in the morning, what is the motivating factor to get you out of bed and go to the office or wherever you're working from? Virginia, would you like to start with that?
There's a lot, but let's stick to a space one. So I'm very excited that we have 35 high school kids who are going to send an experiment to the International Space Station, hopefully in December or otherwise early next year. That is just blows me away that we've been able to provide that opportunity to those students, and I cannot wait to see what experiments they choose to do.
Well, David, you're on mute, so I'll jump in.
Yes.
Virginia took a good one. I think it's, for me personally, it's my colleagues in the Institute, just the most dynamic, exciting, driven researchers and engineers. Everyone just wants to do something cool for the betterment of humanity, and what a group of people to get to work with.
Thanks. Ehud.
Yeah, I'll be the least social among the scientists. I have to say that the thing that excites me most is new results. I have time on a telescope and I wonder, what did we see? And I get up in the morning and get to see the data or the images or the spectra. Now that we're doing lab work and we're testing the instrument and we're running these experiments, I'm eager to see the results. Did it work as I expected it to work? What are the problems? How do we fix them next time? It's really, people who are not scientists don't realize how viable the field it is. I mean, there's new stuff going on every day, and that's just more exciting than anything I can imagine.
Thank you, David.
I come at it from as an engineer and a businessman. It's a very exciting time to be working in space, because we are transitioning from the old way of big government funded projects to smaller, more nimble, privately funded projects, also with government. So it's a very exciting time, and there are many great practical things physically happening, and it's good to be a part of it.
Before I hand over to Ori, who will formally thank our presenters, I'd like to, on my behalf, thank each of you for your participation, but I'd also like to thank the people in the audience who have put Q&As up or made comments. And from all of those, I see that there's going to be a lot of interchange between some of the people in the audience. Well done to all of you who've participated in it. And now it's my pleasure to hand back to Ori.
Thank you, David. I too wanted to thank you all. That was fascinating. I'm sure we could have easily gone for another hour or so. I just wanted to share with our audience that just what's in it for you, apart from obviously learning something new, we hope today. If you're interested to learn more about how to perhaps study opportunities at Swinburne or at Technion, whether for yourself or your kids or your grandchildren, please reach out to me, because I'll be delighted to connect you with our team here. There's also other ways to support our research, and as I always say, we can't all be scientists, but we can all support them, and this is very vital for humanity. So again, if anyone wants to learn more about any of the projects here, please would be delighted to further discuss. Lastly, we hope that you will join us for our upcoming other webinars that we're running. We're running one at the end of the month, the 29th of August, with Professor Andrew Levi from the Technion, who is an expert on research in autism spectrum disorders and epilepsy and impaired learning and memory. He's a Yale graduate, and he's going to share some insight into his research. We'll send you some information about that as well. And I just wanted to sign off by saying that this is sort of, if you want a first date between Technion and Swinburne, we hope that this will grow into something very meaningful, and we'll find some areas. This I'm leaving more with you, Alan, Virginia, and Ehud, and of course David, to identify. But we hope that this will grow to something great, and perhaps we'll do it again in a few months. On that note, wishing you all a good night, and hopefully our lockdown will be over sometime soon. And take care.
Thank you all. Bye-bye.
Bye-bye.
Bye.
Thank you. Bye.
Thanks, everyone. Bye.